Far we have seen the local coordinate frame and how it places a cocoon called the celestial sphere around us, whose upper half contains everything we can see: people, planes, birds, even planets and stars. And the local coordinate frame helps us describe their position precisely using just two angles, the azimuth and the altitude. Now let's see some more concepts related to the local frame. We'll start with latitudes and longitudes, though they are not part of the local frame, but they help us pinpoint the local frame on the Earth itself. So let us start with the Earth, which is a sphere in rotation, and that gives it an axis. An axis being a straight line, it's going to intersect the sphere at 2 points, the so-called poles. So here are our north and south poles. And then we are going to take the locus of points which are at the same distance from the north and south pole. So this locus, this collection of equidistant points from the two poles, forms a circle. And this happens to be a great circle, that is, its center is same as that of the Earth. And what do we call this circle? Well, we call it an equator. So once we have equator, we can have some more circles which will be in planes parallel to the equator's plane. We will call these circles as the latitudes. As you can see, latitudes are not great circles, so they are not of the same size. In fact, they keep shrinking as we go towards the two poles. But latitudes by themselves are not enough to describe a position. For example, if I say I am on this particular latitude, I could be anywhere on this circle, and this is a very huge circle, mind you. So we need something more. So let's introduce some more lines on this Earth forming a grid. These are going to be semicircles starting from the North Pole, ending in the South Pole, whose center would be the same as the Earth's center. So if you will, you may call them as great semicircles. And these two sets of lines on the Earth can pinpoint any location. For example, this location over here can be described to be on this particular longitude and this latitude. And then any observer or any person can describe his or her position unambiguously. So how much of the Earth can this observer see? Well, not much. The view is limited only to a small patch of Earth limited by this circle, the so-called horizon. We'll see how to calculate the size of the horizon. And then everything the observer sees lies above the horizon. So it can be projected onto this small bubble, the upper half of the celestial sphere. In order to calculate the size of the horizon, let us zoom out a bit and put our observer on top of the Earth. I think he's going to like it. So here is the Earth in a schematic diagram, and this is our observer, and we are going to draw a line of sight. As light travels in a straight line, we are going to draw a line from the observer tangential to the Earth's surface. And we can draw this line on the other side too. In fact, we can draw these lines all around the observer, and by symmetry, their points of tangency would lie at the same distance from the observer, forming a circle around him. And this is what we call as the horizon. And the observer can see only those things which are within the horizon. So only this patch of the Earth is visible. So let us do a geometric construction. From the observer, we'll draw his line of sight till it becomes tangential to the Earth's surface, and from there we'll draw a line to the Earth's center and back to the observer. In effect, we are forming a triangle. One side of it is the tangent we have drawn, the second side is the radius of the Earth, and the third side consists of the radius of the Earth and the height of the observer, which may include something the observer could be standing upon, like a building or a hill. Now we know that the tangent to a circle is perpendicular to the radius drawn at that point, so we have a right angle triangle on hand, and we can substitute the values here, like the radius of Earth being 6400 kilometers, and the height of observer standing at sea level could be taken as about 2 meters. And then for this tangent's length, we can use Pythagoras theorem. So let's calculate. I'm going to take 6400 kilometers, these many meters, plus 2 would give us the length of the hypotenuse. Let's square that, and from it subtract 6400 kilometers converted into meters and squared. And when we take the square root, we should get the length of the tangent, which turns out to be about 5060 meters. So, an observer standing at sea level would see the horizon at about 5 kilometers.